In this topic, I shall explain you the concept of electric flux and Gauss's law. So before we come to electric flux, I will explain the general meaning of flux, and let us take an example of water flow. Let us consider that water is flowing in this direction through a pipe, and this is the cross-sectional area of that pipe through which water is moving out. Now, if I want to calculate what is the volume of liquid passing through this area in 1 second, what is the volume of the liquid passing through this area, through this cross-sectional area in 1 second, how will we calculate? In 1 second, it will be, actually it's a cylinder, and if I have given you uniform cross-sectional area everywhere, then it's very simple. We can calculate in 1 second what is the length covered and multiplied by area. It will be actually velocity into this area, because this is the length that is covered in 1 second. So it will give me meter cube per second. The length covered in 1 second and multiplied by area. So volume of the cylinder, and the length of this will be the length covered in 1 second, which is the velocity. So velocity into area, that will give me the volume of the liquid flowing through this area in 1 second. This we call as flux of velocity. Flux of velocity or velocity flux. So it is giving us the volume of the liquid passing through any given cross section in 1 second. Now let me take a different situation. I am taking this ring, water is flowing in this direction, and this is the cross section through which we want to calculate how much water is moving. Then it is V into A. We have just seen whatever is the area of this multiplied by the velocity. Now if I tilt it, then what will happen? You just consider water is moving towards you, and this is the cross section through which we are calculating how much water is flowing. So it is velocity into this cross section area. Now if I tilt it, I make it like this. Now will it increase, decrease, or will it remain same? You see the area has reduced now for you. You just see the projection. Now again the area has reduced. This area, and now it is 0. You might be seeing just a straight line. So this way the area is maximum, and this way the area through which the water is moving, we are calculating this projection only. So it is, when it is coming towards you, it is appearing like this, and then when I move it like this, so it appears like this, maybe it appears like this, and when it is like this, you just see the straight line. This is the projection of it. So it means if the water is flowing like this, and I take this area perpendicular to it, like this, not in this direction, perpendicular to this direction. Like, so what is water? Water is moving in this direction, it's not coming in this direction, so the velocity flux is 0. When it is at some angle, now we are taking the projection only, so it will reduce, it will keep on reducing, and it becomes now 0. So actually whenever we are calculating the flux, how this area is kept is also playing an important role. So flux is, in that particular case I told you it is velocity into area, this is the flux. But here the velocity is perpendicular to this area. So I can say the normal component multiplied by area. So this is the flux of velocity, normal component of velocity into area. Now if it is like this, then it is no longer VA, because I have to consider the angle by which it has turned now, and in this particular case it is 0, because the normal component now, what is flowing in this direction, and I am taking area and the component of velocity in this direction, which is 0. So it will be 0. In this case it is maximum. I have to take the projection. So if it is if the area is like this, velocity in this direction, now velocity in this direction, but the orientation of the surface has changed. Actually, when I say that the quantity V into A is changing by changing the orientation of this surface, I am not changing the area, I am just changing how it is kept. It means now we define another quantity first. This we call as area vector. So we assigned a vector to area also. So if I have to find out the area vector for any given surface, we need magnitude and direction. So direction is taken perpendicular and area magnitude is equal to the given area. So it may be like this, magnitude equal to the given area and direction perpendicular. Now perpendicular direction may also be this or this. This is very case specific. If I take a closed surface, just like a box, cube, cuboid, or even a sphere, then this area vector is outward drawn normal. Right? Otherwise it depends on the particular problem. So in this particular case, water is moving in this direction, the surface is kept like this, area is perpendicular, so this is area, and if I take this angle as theta, so now what is the projection of area in this direction, or I may say what is the normal component of velocity? Component of velocity perpendicular to the surface, that will be V cos theta A. So this will be the flux now. So flux is, this is how we can define flux, normal component of velocity multiplied by area. If it is at some angle, I need to take an angle, or I can simply write it V dot A, dot product of velocity and area vector. So this gives me the flux of velocity, and it is actually giving me the volume of the liquid coming out through a given area. Now we define, so area vector is the vector for any given area. In magnitude it is equal to the area of the surface, and in direction it is perpendicular to the surface. And dot product of velocity and area vector, this gives me the flux of velocity. We can calculate, actually flux is not defined only for velocity, it's too common here. We define it for electric field also. So electric field, what will it be? The normal component of electric field into area. For magnetic field, normal component of magnetic field into area. So this is, we have defined in general actually what flux is. So flux of velocity, normal component of velocity, normal component we are taking perpendicular to the surface, into area. Normal component of electric field into area, that will be the electric flux. Normal component of magnetic field into area, that will be the magnetic flux. Okay, in case of liquid, something is flowing. Now, let me take electric flux. For electric flux, Again, I have taken one specific example. Let me take a point, positive charge. Then electric field lines or electric lines of forces will be outward, radially outward. Now when I told you about flux for liquids, water was flowing and we calculated flux as the volume of the liquid per second passing in 1 second through any given cross section. If I am calculating the flux for the electric field or flux for the magnetic field, actually nothing is flowing here. There is nothing materialistic which is moving out. Unlike in water, unlike in air, where flux is related to the quantity of liquid or gas that is moving out or coming in, whatever. But in case of electric flux, there is no materialistic transfer of something, though there is transfer of, it may be of energy. There is electromagnetic field here and then, okay, but anyway, these are the electric lines of forces, and I have taken one particular charge which is positive and considered one surface. I have taken this one surface actually in such a way that at the top of it, and it's a, I may consider a cone at the top of which this point charge is there, and then from this cone I have taken out one surface. Now if I ask you calculate the flux for this surface 1 and then flux for the second surface, I have told you flux is normal component of electric field into area. So what will be the normal component of electric field for this? If this is say R1 and this distance is R2, this distance is R1 and this distance is R2. Flux for it, electric field will be different. Electric field here, let it be 1 and let it be 2. So E2 and E1, these are the electric fields at these 2 points, and R1, R2 are the distance. I need flux for it. It means I need the area of this part, I need the area of this part and electric field at these 2 positions. And then I want E1A1 or E2A2. Now if we see the angle, electric field is radially outward and so will be the area vector. Area vector is also perpendicular to the given surface. So they are in the same direction. Now one difference, but electric field here is outward in this direction. Electric field here is also in this direction because this is a positive charge. But area vector, I have told you, area vector by convention we take it outward from normal. So for these 2 surfaces, this side area vector there, area vector this A1, A2. So here it will be cos 180 and here it will be cos 0. Now one very important point that I want to tell you here is electric field, as we move away from the charge, it decreases as 1 by r square. What about area? Area of surface is 4 pi r square and it is a part of it. 4 pi r square is the area of the sphere. So this area increases as r square and electric field decreases as 1 by r square. So if I ask you by what fraction E into A will change? E is decreasing as 1 by r square, A is increasing by r square. So actually E into A will not depend on r actually. So this quantity for this as well as for this will be same. So the flux will be 0 if I take it for these 2 surfaces. Net flux, whatever is the flux for this, it is minus EA, it is plus EA, and this will come out to be 0. Now let us define electric flux. E, normal component of electric field, into area vector. Phi is the term that is used to denote flux. So if I have this now as electric field and I want to calculate the flux, again let me take any surface I can take. This is the surface area, so when it is like this, flux is maximum. When it is like this, flux is minimum. Actually, flux here is, it does not denote any quantity, any substance that is moving out, that is flowing through this, but it tells us about the number of lines of forces passing through an area. So how many lines pass through an area? It will depend on what? It will depend on the electric field. If electric field is high, more lines. It will depend on area, and it will also depend how that surface is kept. If it is perpendicular to the electric field, maximum flux. If it is parallel to the electric field, then minimum flux. So surface kept like this, minimum. Surface kept like this, maximum. So if this is, so this is how we define dot product of electric field intensity and area vector, that is called flux. Now if the electric field is not constant in a given region, then we divide the area into very small parts, small areas, so small that for every area electric field may be taken almost constant, and then we calculate it into ds, and then eventually we integrate it. This is the electric flux for a surface with electric field not constant. Okay, now I made a symbol here. This is used if I am calculating it for a closed surface. So this just symbolizes that the surface is closed. Closed surface means it may be cube, cuboid, maybe sphere, spherical, shell, cylinder, any surface which is enclosing certain volume, closed from all sides. This is the symbolic representation for that, E dot ds. So flux for electric field is the normal component of electric field multiplied by the area, or area vector and electric field intensity. The dot product of these two quantities gives us the electric flux. So this, we have defined it exactly on the same lines as we define it for liquids. Though the difference I have told you, here nothing is flowing as such. But this quantity electric flux has been introduced because it is very useful quantity here to help us to calculate the electric field due to different types of charge configurations. So far we have done electric field due to point charge. Then we apply the same to find out the electric field due to an electric dipole. There also we used Coulomb's law. Superposition principle, we calculated field due to one charge, field due to second charge, and then find the resultant. But if I give you, find out the electric field due to a charged shell, due to a charged cylinder, then again we can apply Coulomb's law. We can divide that shell or the wire into very small parts, calculate the electric field due to that, and then integrate it. This will be one approach. Another approach will be Gauss's law. It helps us to calculate the electric field due to different types of charged configurations, and especially when there is symmetry. Let me take a point charge again, Q, and calculate the flux of this point charge for this sphere. Let us draw a sphere of radius r. I want the flux for it. So we have to calculate the value of E dot A. and I want it for the entire surface. So I may divide it again into very small areas, E dot ds, and then integrate it to calculate the flux for the whole sphere. I may take only one very small area, say ds, at any point I may consider it here. Calculate the flux for it. Okay. Flux is electric field into area vector. See, both ds is always perpendicular to the given area. So whatever part we consider, area vector will be radially outward, perpendicular to this, along this radius. Electric field is always force on positive charge along this line, away from it. So the angle between them is 0 actually. So flux is E ds cos 0. Cos 0 is 1. Okay, what is the value of the electric field here? It is 1 by 4 pi epsilon naught q upon r square and ds. Now, if I integrate it, 1 by 4 pi epsilon naught is constant, q is also constant, even r square is constant because r square means the radius. For different ds, r is same for all because every part on that sphere is at same distance from the center. It is just the radius and integration ds. Now integration ds is the total area of that sphere. Its value will be 4 pi r square. So 1 by 4 pi epsilon naught q by r square into 4 pi r square. And what it becomes? 4 pi r square q by epsilon naught. So E dot ds is q by epsilon naught. So the total flux for a closed surface is equal to 1 upon epsilon naught times the total charge enclosed by this surface. It's very important, Gauss's law we call it. And now for this, we have derived it particularly for a spherical surface enclosing a point charge. But this is valid for all types of surfaces, not just for spherical. Had we taken some other shape, even then this flux will remain same. So this is valid for all types of surfaces, not just for spherical. On left hand side we have electric field, which will be the value of electric field on that surface. Q is the charge enclosed. E is the net field on that surface due to all charges, inside or outside. But this Q is only enclosed charge. So this is enclosed, this is the net field on the surface, this is valid for all types of surfaces. Further, this has been derived from Coulomb's law. So it is true only if Coulomb's law is true. So it basically follows from the Coulomb's law. We have made use of that 1 by 4 pi epsilon naught q by r square. This has been derived using Coulomb's law. So E dot ds is q by epsilon naught. It is valid for all types of surfaces. E is the net field on the surface, q is the charge enclosed, and it follows from inverse square law actually. And one more very important point, that we have applied it on a surface, and this surface we call Gaussian surface. Gaussian surface. So whenever we have to find out the electric field, now I am telling you a general way to calculate the electric field. We have to draw a surface which will be called Gaussian surface, and we are free to choose any surface. So we will always prefer to draw a surface which is symmetrical. Symmetrical in nature means we will take it in such a way that electric field on each point of the surface is same, so that this can be taken out of that integral sign. It will be easier to calculate. It doesn't mean that we can't calculate for other surfaces. We can. But we will prefer always a symmetrical surface so that it is easier to calculate. And so that surface will be called Gaussian surface, and this is simply hypothetical surface. We are assuming it for our own convenience and to apply Gauss's law. So that's all in Gauss's law. So now we will take up the applications of Gauss's law. We shall take up the electric field due to a charged wire, shell and a charged plate. Thank you.